So now we're going to transition to talking about what exactly is going on in the brain that allows you to attend to things out in the world, and exactly what changes in your brain, where do these attentional signals come from, and so on and so forth, okay? And so if there's one basic idea that I want you to get when it comes to the relationship between attention and the brain, it's this notion that attention amplifies neural signals in the brain, okay? So at any given moment, your brain is processing information in a lot of different domains: vision, olfaction, touch, all these different domains. And what attention will basically do is it will pick some sort of signals in the brain that are bouncing around and will just accentuate them. Because again, remember, attention is intended to select some information for further processing at the expense of others. So if you're in a room and someone's like, hey, do you smell that? And you go like, what's that smell? What your brain will do is amplify those signals associated with olfaction and smell, and it might not, it's not going to amplify, or it might even in certain cases actually suppress signals associated with audition or vision and so forth. So to give you a sense of how this works, let's go back to this experiment that we were talking about in the last section. And this is the one where we can see this effect as a function of attention. And the question that some researchers asked was like, okay, well, what ends up going on here is this idea that, I point an arrow, before the target comes on, your attention shifts to a particular location, and then you can do the task, okay? So then they asked the question, which was just simply, what happens after the cue, but before the stimulus? Like basically what's happening in this gap period, okay? Like what can we see going on in the brain when you're shifting your attention to a new location, but before the actual target comes on? Can you already see some amplification of that location as space? And so if you were a participant, you would see a screen like this. You would see a screen like this while you're lying in the scanner. Sorry. And you would then see a little arrow appear and disappear. And it turns out that what you can do is you can just look in early visual cortex, like in some region like V1, and you can see that in a situation like this, when a person is attending to the left side of the screen, you can see that this part of the visual cortex is going to light up, okay? So when you're attending to the left side of space, you're keeping your eyes here, so your eyes haven't moved, it's just your attention that's moving. When you attend to the left side of space, your right visual cortex starts to get activated, okay? Even before there's anything on the screen. So it's almost like during this anticipatory phase where you showed the arrow that pointed you over to this side of space, your brain is already accentuating and highlighting and amplifying this region of space, even though there's nothing there. Now, just as a reminder, why is it that when you're attending to the left side of space, the right hemisphere is getting more active? That's because if you remember, there's this sort of crisscross aspect of visual processing in the brain where stuff that's on the left side of space gets processed by the right hemisphere, stuff that's on the right side of space gets processed by the left hemisphere. So if I tell you to attend to the left side of space, the part of your brain that's going to get amplified is going to actually be early visual cortex in the right hemisphere. And so that's what's going on in this little plot right there. And then similarly, just for balance, you can flip it where you can tell people, okay, now I want you to attend to the right side of space. And sure enough, you see an amplification in the visual system of the left hemisphere, okay? But again, this is all before a stimulus appears. So what this is telling us is that even in the absence of a stimulus, what you can do with your brain is pick locations of space, pick certain regions of the world, and kind of amplify these in anticipation. That's what's explaining the sort of results that we saw a little bit a while ago here, which is once I show you an arrow like this, even before the little target comes on, your brain is already kind of revving up the engines in anticipation of the target coming on. And that's why also if I point your attention in the wrong direction, you can see that it's going to come at a little bit of a cost because you're amplifying this region of space and you're going to have to switch over to the other region of space, okay? Now, attention, though, can also increase the strength of a signal that's related to a stimulus, though, that is present. It's not like attention only operates in regions of space when there's nothing there. So you can actually also see this amplification process for signals that are currently being processed by the brain. So for example, in one such study, you're a participant in a scanner and you would see displays like this, okay? And what I would tell you to do is I would tell you to either pay attention to the houses, pay attention to the two faces, or pay attention to these colors, okay? And you'd have to make little judgments. So for example, the judgments could be like, are these the same house or different houses? Are these the same two faces or different faces, and so on and so forth. And in this particular study, what they did is they said, okay, what we're going to do is we're going to get people in the scanner. We're going to have them pay attention to the houses, then the colors, and the faces, and the colors, and the houses, and the faces, and the colors, just bouncing back and forth from one trial to the next, what they're paying attention to. And we're going to look at what happens in the FFA, okay? So here, what I'm showing you on the vertical axis is the activation in the FFA. And here on the horizontal axis is time, okay? So this is like 0 seconds, 11, 22, 33 seconds. So a minute is about here, 2 minutes is right around here. I don't know why it's numbered that way, but whatever, you get it. Okay, and so what H, F, and C stands for is faces, colors, or houses, okay? And this is a really critical bit, okay? Really pay attention to what I'm about to say. The stimuli on the screen do not ever change, okay? So it's not the case that you show only faces or only houses or only colors. The stimuli is staying the same. The only thing that's changing is what you are paying attention to, okay? And this is important because what's going on is you can see that as you tell people to pay attention to different things, the FFA will turn off and on accordingly. So when I tell you to pay attention to the faces, it really amplifies the face signals and the FFA gets really active. When I tell you to pay attention to the colors, okay, the FFA doesn't care so much about colors, and so it's going to shift the pattern of activity because, again, what attention is doing is amplifying sub-signals at the expense of others. Similarly, you can see houses aren't really going up, but you could imagine that, for example, the PPA might get really excited when I tell you to pay attention to houses while the FFA, while the response to faces would drop. Now, why is it so critical that the stimuli on the screen don't change or didn't change in this case, okay? Why is it critical that the experimenters didn't do it by showing you pictures like this or pictures like this? The reason is because if you were not just changing what you told people to attend to, but you were also changing what they saw, you would have two different things that were changing, and that would be a confound. So you could get these different patterns of results, but someone could say like, wait, is that because you're changing what I'm attending to? Or is it about because you're changing what I'm seeing in the world? So when you're doing an experiment where you want to manipulate something like attention, you've got to keep the stimuli constant. And the only thing you want to change is what the person is attending to. Make sure you really understand that idea. It's a very important idea about this notion of confounds and isolating the variable you're interested in. If you have any questions about it, it's certainly a great thing to bring up in discussion section. Another natural question that people often wonder about attention is, can you see these effects in other modalities besides vision? The answer to this question is always yes. I referenced it a little bit ago with the concept of if someone's like, hey, do you smell that? But I'm going to show you a simple experiment from audition. So just as a reminder from what we talked about a little while ago, in early auditory cortex, you don't get spatial retinotopic maps like you do in vision. You get these tonotopic maps where the red and orange parts of the brain respond to more low tones. And then as you move from the red and orange areas to the green and blue areas, you can see green and blue over here, it's responding more to high tones. So as you move across the cortex, you've got regions that are more or less selective to like the pitch or the frequency of the tone. And to make it really clear, you can see something like this. So if this part here really likes the low frequencies, this part here really likes the high frequencies and so forth. So in this particular experiment, what they did is they put people in the scanner while they had headphones on, and there would be two frequencies in both ears. There'd be a low frequency in one ear and a high frequency in the other. And what you would do is you would just have people alter what they're attending to. So the tones in the ears don't change, but you would have them attend high, then attend low, then attend high, and attend low, and so on and so forth. So the question is, what's going to happen in early auditory cortex as you vary what people are attending to? So again, on the vertical axis, you're looking at the signal change, the activation differences. And on the horizontal axis, again, it's time. And then what these lines here are telling us is the response to the 250 hertz voxels, which are the low frequency, and the 4000 hertz voxels are the high frequency. So take a second and think about what were you going to predict that the responses are going to look like, okay? As you're changing what you're attending to in auditory cortex, or as you're changing what you're attending to in audition, what changes are you going to see in auditory cortex? Hopefully, you were imagining something that kind of looked like this, where you see that there's this sort of crisscross type of effect again. When I tell you to attend to the high frequency voxels get really excited. When I tell you to attend to the low frequency voxels get excited. And it's this just sort of crisscross thing again. And once again, as was the case before, what you're hearing is never changing. The only thing that's changing is what you're attending to. So this is just showing that same sort of pattern that way we were talking about in vision. You can see this crisscross here, this rising and falling in auditory cortex as a function of what you're attending to, similar to what we were seeing here in visual cortex, this rising and falling as a function to what you're attending to. So the same principles that you can see in vision, you can see in audition, you can see in somatosensation and touch and olfaction and gustation, all these different modalities. But just because we've been building off of it, I'm mostly focusing on vision. Okay, so this is what I mean though about attention amplifies neural signals in the brain. So if you're looking at a scene that has, for example, a face and a house and colors on it, if I tell you that I want you to attend to these faces, the face signals in your brain will get amplified. If I tell you to attend to the houses, the house signals in your brain will get amplified, okay? But an interesting and important question though is, where does this amplification come from in the brain, okay? How does the face signal get amplified? It doesn't just kind of come out of nowhere. So what are the mechanisms that allow the face signals to get amplified, okay? The basic idea is that the signals start in the frontal and the parietal lobes and will effectively reach back and amplify those signals. So you can almost think of it as like sort of a spotlight metaphor, where you can think of it as like there's, little people in the front of your head or in your parietal lobe. And what they'll do is they'll shine a spotlight on different parts of your brain. They'll shine a spotlight on the face parts of your brain. They'll shine a spotlight on the house parts, on the low frequency, on the high frequency. So they're the little guys up here in the front of your brain. And what attention is doing is reaching back into your sensory cortex and shining a spotlight and amplifying certain regions that you want to attend to. So for example, here's a case from vision. So this is V4, which we talked about a couple weeks ago. And then HIS is a region. This is one of those locations of a region in the front of the brain. That's like the home of the little spotlight. FEF stands for frontal eye field. And that's just a part of the frontal lobe that's involved in attention. And what they do in these particular studies is they get monkeys and they put electrical grids, like electrodes from electrophysiology, in both V4 and the frontal eye fields. And then what they'll do is they'll find neurons who have overlapping receptive fields, okay? So what I'm showing you in the solid outline are the receptive fields from a frontal eye field neuron. And then in the dashed line are the receptive fields from a V4 neuron. So right now, for example, actually let's focus on this one. You can have two neurons, one in the FEF and then one in V4, but they're both going to be able to see the same thing. They're both looking at this little red guy, okay? So two different neurons or two different collections of neurons, but have receptive fields focused on the same thing. And so in this particular task, if you are the monkey has been trained to do a pretty simple task. You will see a fixation dot, and then a bunch of colors come on. And then what you'll do is you will grab a lever, like a little bar, and then when this cue comes on, the cue is telling you, hey, pay attention to the red one. And then as soon as the red one changes color, you let go of the bar. That is the whole task. So you're the monkey, this comes on, you see you're holding the cue, or not holding the cue, pulling the little bar back, you're holding the lever, you're told, hey, pay attention to the red one. You're like, okay, I'm now gonna shift my attention to the red one. That's a really important thing, that when this cue comes up, you're shifting your attention to the red one. And then when the red one changes, you let go. So you could make this dot green, you can make this dot blue, okay? Super simple attention task. The only goal here is just to get the monkey to shift its attention to one of these dots in particular. And by making it red, you can get the monkey to shift his attention to the red dot or the green dot or the blue dot. And then what you can do is you can look at these neurons in V4 and frontal eye field once the monkey shifts their attention. So the moment the cue comes on, you can ask what goes on in these neurons. What is happening to V4 and frontal eye field neurons when the monkey is shifting his attention, okay? And this is what you see, okay? About 80 milliseconds after the cue comes on, that's what's going on at time 0, time from cue onset. So as soon as this cue comes on telling the monkey, hey, shift your attention here, you can see that the signal for the red dot gets really amplified. So 80 milliseconds later, the neurons in here are like, oh, pay more attention to the red dot, pay more attention to the red dot. Whereas in V4, you don't see that same boost until 130 milliseconds later, okay? So you can see this sort of stepwise processing sequence where at first you get this amplification signal from the frontal eye field that reaches back and then amplifies the representation in V4, okay? So this is why I say that it starts in the frontal or sometimes the parietal lobes and then reaches back into the brain to amplify them. Because first you see, oh, the frontal eye field is getting excited by that signal. And then V4 is subsequently a few hundred, or I guess 50 milliseconds later is getting, amplified by that signal, okay? And it actually turns out, we won't really go into it, but just to make it point, you can actually do these studies where you kind of cut the connections between the frontal eye field and regions like V4, and you actually can see there'll be this early boost here, but then there'll be no subsequent boost in V4 because the signal basically has nowhere to go from the frontal lobe. Okay, so again, that's where this notion of reaching back to amplify signals comes from. So that's top-down attention. That's where the monkey is like, oh, I want to shift my attention over there. But there's another type of attention that we talked about, which was bottom-up attention. So what exactly differentiates bottom-up attention from top-down attention in the brain? So this is another study from monkey electrophysiology. And so what happens here is you're the monkey, you're looking at this little fixation dot to get started, and then a line will come up, and that colored line is the target. So this is a really simple visual search task. Remember how a little while ago we were doing the thing with the vertical green bars? It's a task like that. So you see, okay, this is the target that you're looking for. There's a little bit of a delay. And then in this particular trial, this is a pop-out trial where, you know, it's pretty easy to spot that this is the target right here, okay? And what the monkey does is the monkey just looks at the target. So what's going on is this is where the monkey's staring. This is what the red circle is. And then, you know, a little bit of time later, it doesn't take too long, the monkey shifts its eyes and looks over there. So this is a pop-out type of trial. This is a bottom-up attention scenario. And they compared it to a top-down attention scenario where there's the same target in the same location, but this situation's a little bit longer. That's why the reaction time arrow here is longer, because it's going to take the monkey a little bit more time to find the target in this situation than it is in that situation, okay? So the question is, what is going on in the brain when you have situations of a stimulus popping out in this bottom-up way and a stimulus not popping out, but the animal finds it in this top-down type of way? Okay, so now, similarly to just before, we're going to look in FEF, and we're also going to look in a nearby region called PFC, prefrontal cortex. So these are our frontal lobe regions, parts of attention. And then here, LIP stands for lateral intraparietal region. But you can really just think of it as the frontal regions and the parietal lobe regions, okay? So even though there's three of them, for our purposes, what we really care about are the two frontal ones and the parietal lobe region, okay? So over here, we're looking at what's going on in the pop-out situation, okay? And so what we're seeing on the vertical bar is neurons firing, and then on the horizontal bar is time, okay? And what's going on is that at time point 0, that's when the animal makes the saccade. That's when the animal, sorry for the animation, that's when the animal moves their eyes, okay? So what we're gonna do is we're gonna see, okay, we know when the animal moves its eyes, let's then look backwards in time and see what's going on before the animal actually makes an eye movement, but is shifting their attention around accordingly. And what goes on in the pop-out situation is something like this. Now, this is an overwhelming plot. There are a lot of bars, there's a lot of lines, but there's just one thing that I just want you to get out of this plot. And that one thing that I want you to get out of this plot is the fact that the first part of the brain to pop up significantly is this blue region, the parietal lobe region, okay? First, the blue region kind of gets off baseline, and then you can start to see that the frontal lobe regions, which are in green and red, they come second, okay? So from this graph, the big thing I just want you to see is first blue, then green and red, okay? In this visual search situation where it's a top-down case, where it doesn't just pop out, we see a very different pattern of results, okay? The first regions that pop up in terms of getting activation are the green and the red, and then the blue. So over here, it's blue, then green, red. Over here, it's green, red, then blue, okay? Why would that be? Well, if you look at this little schematic, which I like quite a bit, we can get a pretty good sense of the way the attentional network works. The idea being that when it's a bottom-up attention type situation, let's follow the dashed line, the signal comes in through the visual system, goes through the parietal lobe, and then reaches the frontal lobe. It's almost like there's this sequence here of first blue, then red, which is exactly what we're seeing here. First blue, then red and green. I should have said red and green, sorry. Whereas when it's a top-down type of situation, we can see that the signals start in the frontal lobe, and that's what these solid lines are, and then they reach back into this blue region, which can ultimately then reach back into the visual system. So first red and green, and then blue. And then over here, first red and green, and then blue, okay? So the idea of what's going on is that these different attentional network regions will both play a role in processing top-down and bottom-up attention, but in a different order. When something's like a tsunami that's going to hit you in the face, metaphorically speaking, of course, like a sound that pops out or a color that pops out, it's going to just rush like a big giant wave through the visual system, through the parietal lobe to the frontal lobe, okay? It just kind of like rolls its way through. Whereas when something is more top-down attention, where you're going to be the one moving around until the spotlight gets where you want it, it's going to be a wave coming back down the other way. You're going to have this signal in the front of the head that's going to start here in the frontal lobe, move to the parietal lobe, and then move back into the occipital or temporal lobe where the visual system is, okay? This is usually I'll let you know, whenever I teach this section, I know that this is an experiment that's particularly complicated. It's really cutting edge cognitive neuroscience. So if you're a little unclear about it, definitely write down some questions. It's usually one that in class we'll stop, clarify a bit. So this is a good thing for probably talking about during discussion section. Okay, so we'll stop this little unit there. What we're going to talk about in the last section on today's lectures, or this week's lectures about recognition and attention, is going to be this question about what happens when you damage these attentional networks. Come back, be excited. I'm excited because I'm going to show you some patient results, some video clips of people who have damage to their attentional network, and their behavior is going to be probably quite different than you would ever anticipate. So see you soon.